All right, we're going to spend some time talking about the different properties of states of matter and what they have to do with intermolecular forces. So just a recap on chemical versus physical processes, or chemical versus physical change. So a chemical process is one that involves the breaking or formation of new bonds. So a chemical reaction would be a chemical process. If we think of something like rusting, so we've got metal turning into iron oxide, so that would be a chemical change. We're changing the identity of the chemical. A physical process, though, is one where normally we're just breaking weak intermolecular forces. So when we go from a solid to a liquid, or from a liquid to a gas, or sometimes we form weak intermolecular forces. So if we go from a gas to a liquid. And there's actually debate on whether or not dissolving a salt would involve a physical change or a chemical change. Now, if you think about it, we're just changing it from a solid into a liquid, but not really. We're taking a solid and we're breaking it apart into its separate ions, which is kind of like a chemical change because we're breaking bonds. Also, when this happens, we've seen before that when we dissolve ionic salts in water, it usually generates heat or it takes in heat, so it's an endothermic or exothermic process, which usually indicates that the chemical reaction has occurred because we've generated or taken in energy. But think about it, if you've got salt that's a solid, or you've got salt that's dissolved in water, they taste the same. So chemically, has it really changed if salt tastes the same dry as it does when it's dissolved? Oh man, we could puzzle on this for days. Anyway, let's just talk about the process of changing from one state of matter to another. And so here is a heating curve. So this little scale right here shows the process of going from a solid all the way up to a gas. And this can go either direction here. We don't have to go forward. We can also go backwards on this, so we can go from a gas down to a solid. So as temperature rises and the energy increases, we can see kind of what happens. And so this down here, this would be the enthalpy, so this would be the joules that it intakes. So when we've got a solid and we heat the solid up, it's going to gradually increase in temperature as we add energy to it. Eventually it's going to hit this point right here where it flatlines, which means its temperature does not increase. This would be the delta H, the change in enthalpy of fusion, commonly known as melting and freezing. So for example, if this was pure water, that point right there would be 0 degrees Celsius. It's the point where the water both freezes and melts. So when we apply heat, it's going to get to this point, and at that point, all of the energy that we put in is going to go to breaking apart those bonds and turning it into a liquid. So it's not going to increase in temperature. You can't have a piece of ice that's any higher than 0 degrees Celsius. So the entire piece is going to melt before anything's going to increase in temperature again. But then once it's all melted, it will increase in temperature again at a steady rate until we hit this point right here, which is the change in enthalpy or vaporization. That's the point where it boils. It's also the point where it condenses. So this would be, if it's liquid, or if it's water, 100 degrees Celsius. So at that point, if we're boiling water, if you put a thermometer in boiling water, you cannot get boiling water to go above 100 degrees Celsius, pure water that is. And so it's going to stay there until all the water's boiled off and turned into a gas. Once it turns into a gas, then we can increase its temperature as usual with the addition of heat. And we do the same process backwards. So 100, cool down to 100. It's going to condense and it'll all stay at the same temperature until it's all condensed. Cool it down and it'll freeze and it'll all stay at 0 degrees Celsius until it's all frozen. And then we can reduce the temperature of the solid. And these two values right here, they would be the same no matter what direction you're going. And what those indicate, so delta H would be the change in energy to melt or, in that case, freeze 1 mole of the liquid or solid. And so if it's water, it would be the amount of energy required to melt or freeze 1 mole of water. Same thing with this one up here. It'd be the change in energy required to boil or condense 1 mole of a liquid. And so if it's a positive value going forward, because we're putting energy in, it would be a negative value going backwards. Same amount though, same magnitude. Now the true story. So on that cooling curve, there is one little truth that's not shown on there, and that is supercooling. So when we cool a substance down, some of them will actually go through a process that's called supercooling, where it will drop below its freezing temperature, but not actually solidify. So it'll stay a liquid below its own freezing temperature. Once it hits this dip down there, though, that would be the point where crystals start to form. The formation of crystals actually warms the solution up, which will jump it back up to its freezing point, and then from there on out, all of it will start to freeze, and then it'll solidify again. So here's a slide we've seen before. This is just to remind us how a solid looks. And so all the molecules are going to arrange themselves. In this case, we're looking at some polar molecules lining themselves up, negative to positive dipoles. And we're going to have those intermolecular forces. Those would be dipole-dipole bonds that are holding it together in this structure. Now we could have this with London dispersion forces, ion-ion, hydrogen bonds, any of them, and it's going to have kind of the same idea where they'll line themselves up according to charges or according to intermolecular forces. But with solids, we do get that regular repeating pattern. And that's a result of the dipole-dipole in this case, or any other intermolecular force. Now we'll talk about that point where it flatlines on the heating and cooling curve. That was the delta H of fusion, so the heat of fusion. This is the energy required, absorbed when 1 mole of a solid liquefies. And we know the more heat, the more motion, and so as those molecules are heating up, they're going to start moving around, and eventually we're going to get to that point where those molecules are moving to where they'll break off and actually sever those intermolecular forces, and that's the point where it has liquefied. And this process to melt something is always endothermic, so it's always going to take in energy. And the temperature flatlines at this point because as the energy is coming in, it's going to be used to sever all of these intermolecular forces. So the energy, like this one up here that's moved off already, energy is not going to go towards that guy. It's going to go towards these other guys first. But if we were to cool down a liquid and get it to freeze, the amount of energy that is released when it is melted would be gained when it was frozen, in which case it would be exothermic, so it would be a negative value. Now if we compare the last slide, which was looking at dipole-dipole, to an ion-to-ion bond, they're going to have much higher melting points, and the reason for that is because the intermolecular forces that are holding them together are much stronger. This is why something like water melts at 0 degrees Celsius, but something like sodium chloride melts at 1,000 degrees Celsius. It's going to take a lot more energy to sever the intermolecular forces in an ionic compound than it does in a regular or polar compound. Alright, so we've warmed something up, we've got it melted, now we are in the liquid state. So we can see these molecules, they're not as neatly arranged and they're actually moving around. We can't see it in a frozen slide, but if you kind of move your fists around each other, you're going to see how a liquid behaves. So they're sliding around, they are changing intermolecular forces. And those forces are strong, but they're not going to be as strong as they are in a solid because we don't have that repeating stiff pattern. Okay, so the energy of vaporization would be the energy going in, and this is where we're actually snapping those intermolecular forces, and they are gone from each other. Going from a solid to a liquid, we're breaking, but then the intermolecular forces are kind of reforming. They're just weaker. In this case, they're gone from each other. Gases have no intermolecular forces between them as far as we're concerned. This process is also endothermic. It's the amount of energy per 1 mole that is vaporized. However, if we were to go backwards, if we were to condense, it would be exothermic, which means it would release energy and it would be the same magnitude. So when you sweat, this is why it cools you down, because it's an endothermic process. It takes energy and it's taking that energy from your body, which as a result cools you down. So thank you, dipole-dipole bonds, for keeping us cool in the summer.